T-minus 10, 9, 8, 7, 6, 5. All three engines up and burning. 2, 1, 0, and liftoff.
Imagine being able to light up an entire city, or a vast expanse of land. We are talking about 60 square kilometers at any time of night. But not with generators, batteries, or conventional artificial light. Instead, with sunlight reflected from space. This technology, which seems like something out of science fiction, is already in development and could radically change everything from how we respond to emergencies to how we grow our food. Today, we are talking to Ben Nowack, CEO and co-founder of Orbital, the company that wants to turn this vision into a shiny reality.
Ben Nowack.
Pablo,
Nice to meet you.
great to have you here.
Well, Ben, thanks for inviting us. When I first heard about this project, I said to my team, we need to take a plane, come here, because you guys are doing something really special. Tell us about it.
Yeah, it is a dream to come to work every single day, I can tell you that much. We are providing sunlight at night for the first time ever, and we're doing it with satellites. So humans have control over basically every resource, right? We can, mine for any metal we need. We can collect rainwater, divert rivers, make giant dams, do whatever we need to for water. But we currently have no control over where and when the sun shines. We just kind of, use daytime for everything to get around, for solar power, for all kinds of things. But at night, we don't have that at all, and we end up just using fossil fuels. So what we're doing here at Reflect is we are bringing that sunlight to the world as if it's a resource. And it's kind of like we're tapping the sunlight in space and then bringing it to the Earth. So we redirect sunlight from space and bring it down to the world. And the original idea for this actually came from just looking at a map of the differences in sunlight you get around the world. And I was just trying to come up with different ways to move sunlight from one place to another and do that in the most efficient way possible. And after a couple months of work, I ended up figuring out the idea for Reflect. And I did all the math for it, and it actually worked quite well. So I was pleasantly surprised and decided to start a company. Before that, I always knew I was going to start a company one day. So I was kind of training for a number of years. And in high school, I had a YouTube channel called Ben Builds, where I would build like RC planes, long-range drones, X-ray machines, like YBCO superconductors. And one of those things was a fusion reactor. In building the fusion reactor, I kind of realized that the sun is a lot better at fusion than we'll ever be. And fusion is always pitched as the thing that's going to solve the world's energy problems. And when I built that thing, I was kind of like, wow, maybe it won't be fusion actually. It's pretty hard to match the smoothness and the pressure you get in the center of the sun. And that fusion reactor I built was kind of more of an art project. It was just one of those Farnsworth fusers. Made some neutrons out of deuterium and made some helium from that. But it was like, very, very silly, like the things we made, back in the 60s that we abandoned a long time ago. And even the fusion reactors today are, I think they have a long way to go. And I just kind of realized like, maybe there'll be other things. So I started, working on antimatter for a little bit after that. And then after doing that, I realized I should just take the normal path, get a mechanical engineering degree, and get some cool internships. So I worked at SpaceX for 2 internships. That was an incredible experience. Got to work with one of the best teams there and learned just so much that I've kept with throughout my life. They really are so mission driven, and I don't know, just the education you get from working there for a couple years is insane. And then after that, I worked on a number of startups and looked into probably about 100 different ideas, trying to increase my rate of iteration by having creative ideas but then killing the ideas very quickly. I feel like some people like have an idea for a company and then they'll sit with it for a couple years without ever really testing it, and as soon as you start testing the idea you think is great, you realize it's actually really stupid, and you have to do it all over again. And you have to do that over and over again for years before you end up actually having a good one. So before starting Reflect, I was probably like 15 or more years and like 100 different ideas, and basically all of my personal money. I actually optimized my life around being ready to go homeless if I started a company. So I lived in a Mazda Miata for 3 months just to practice being homeless, so that I wouldn't be afraid of running out of money when I did start the right company. So I did all kinds of stuff like this, just to kind of get ready for what I knew would be a long slog of crazy ideas. And then actually it's been great, much better than I expected starting the company. And yeah, we've come a long way. So this time last year we were about 3 people, and we were in a pretty small office. We had finished hot air balloon testing, and all of that worked quite well. We reflected sunlight from a mirror on a hot air balloon down to some solar panels, and that worked quite well. And then we were able to raise some capital, and now we're working on the first satellite, which you can see, one quarter of the reflector behind me. But yeah, it worked really well. And that was kind of the physics proof that we wanted. We had done a bunch of ground testing and done all the math, but we really wanted to try the whole aiming system from a moving target, because all the jitter of the mirror was things that people were concerned about. So we wanted to make sure that we had that just ground home. And then we released a short video, obviously, which got 55 million views across a number of reposts, and we ended up with 264,000 applications, and that gave us the use cases. Because the original concept for this, it was just energy, right? I was like, you could use this to power on solar farms. There's $3 trillion of them, and you could materially replace fossil fuels with something like this. It actually can exist at that scale, whereas very few other energy technologies can actually exist at that scale. So that was the original idea. It was like, that's $1 trillion market. If we can make one satellite break even, we can definitely make that work. But then when we released that video, we got, insane inbound from all around the world, 157 different countries. And it just everything under the sun. You could just, search anything in our database and find somebody asking for it. Tons of people in Scandinavia and Norway asking for sunlight to improve seasonal depression, right? In the middle of winter when it's super dark. People get really sad, and a lot of times they'll actually fly south for a couple weeks out of the winter. With us, you can actually stay home, and we can just light up your town, which is great. And so we got a lot of that. A lot of places actually have poor lighting infrastructure. So if you already have streetlights, you don't really need our service. But if you're in a new place that hasn't been able to build streetlights yet, the use case there is insanely valuable, right? You're actually able to see at night. It's a huge security add when you're able to walk around at night and feel safe. But then I think the even more important use case is, or an even more important early use case that's critical, is we're able to light up anywhere on Earth in under 30 seconds. So not only can we add light anywhere but without any infrastructure, but we can do it very quickly. So when you have these constellations, I'll just show a quick model. When you have a constellation of satellites orbiting overhead, the Earth's spinning right by, and from these satellites that are always overhead, if somebody needs sunlight in an emergency, we can just rotate the satellite and light up a whole 6,000 acre area on the ground. So that was a new use case. So not only can we provide sunlight around the world for all the things we use sunlight for, 99% of life on Earth relies on sunlight, unless you're like a thermophile or something like that. You rely on sunlight, the plants grow, animals eat the plants, we eat the animals or the plants. It's all sunlight powered, even fossil fuels are all sunlight powered. And we're adding that, but also we're adding it very quickly and very precisely in a controlled way. So if there's an emergency, even in the middle of nowhere, in the middle of the ocean, we can light up a whole area, allow people to see. You don't have to wait for a helicopter with a searchlight to get refueled. We're just there. As long as you can get in touch with us, we can light up that area. So there's a huge amount of utility to add with this responsive constellation.
So how many of those ideas, use cases, you guys came up with versus the applications that came through, and then you say, oh, it can be used for this, it can be used for that? Because I guess that some people came up with creative ideas that you never thought of, right?
Yeah, absolutely. I remember before, like, about this time last year, we had a list of about 60 different use cases. And I think the list, we probably went up by about 20 after we had all the applications come through. So yeah, it was pretty extreme. Yeah, like people, we got some funny ones, like help me dry my laundry. We did not think of that beforehand, right? So that was pretty funny.
So it could be used for things like agriculture. I mean, I spoke before coming here. I spoke to some friends of mine who are, working in the field, and I asked them, what do you guys think of this idea? And they said, well, it has many use cases in places like England or in the Netherlands where it rains a lot. The roots from plants and crops, they suffer from humidity, and this could be something useful. And they found that even a few minutes of extra light could help, build healthier and more productive crops. So agriculture is one of those use cases. Obviously, you mentioned already safety. Yep. In case of an emergency, earthquakes or something, all the power goes off, and you guys can reflect light and help support, all the rescue teams to find people. Obviously, military comes as also an option, I guess, in operations where probably you don't want dark, but there are many other things like events, right? You could actually light up an event and make it more fun.
Yep.
So a lot of interesting area.
That. Yeah, especially for the first satellite, it's going to be so new that you can't help but build a giant event around it.
Yeah, so you have a lot of momentum going. You have recent investments. Investors are trusting on this product. And so tell me, what are the next big milestones for you guys? What is the timeline? Because I've read that you intend to launch your first satellite in 2026 and have like a kind of world tour where you will light up like 10 iconic locations. Is that right?
Absolutely.
So have you defined what those locations will be or where?
We haven't defined the locations yet.
Okay.
There's something of a bidding war going on right now for who's going to get one of those 10.
Okay.
But yeah, we're launching our first satellite next spring, or as early as next spring, we like to say, because sometimes missions do slip. But yeah, as early as next spring, we're launching our first satellite. It's going to be about as bright as a full moon. Actually, it might be about 5 times brighter. The team's been doing an insane job over here, but we're saying brighter than a full moon for about 4 minutes. And actually, it'll be a 17-minute total pass, but 4 minutes at its brightest. So yeah, we're launching that next year, and each of the world tour spots is going to be about a week apart, so people have time to travel between them and go and watch it. And it'll be at historic places all around the world. And it's actually kind of funny because getting from one place to another, like I've flown around the world talking to people since then, just thinking about like how big the Earth is for a plane to fly around, but the satellites fly over every 94 minutes. And if you do a ring of satellites, they're just constantly there around the whole world. So it's, I don't know, since traveling for this, I've really developed a greater respect for actually what's happening with these vehicles. So while we're doing the world tour like a week apart each time, you could do them all in one night. The vehicles are capable of that, but we're spacing them out so folks can travel and see it and really, to amplify what we're doing here and the impact that we're having.
Ben, different concepts have been thought about in the past. I mean, we can go back to the 1920s. Scientists in Germany, then the Russians came back with that project, Znamia.
Yeah.
Znamia. They even launched Znamia 2.0 and it worked.
Yep.
And even NASA had some plans with Solaris, and other companies, other scientists have been, thinking about this for a long time. What are the things, especially from the Russians who got actually, got it in space, and they they got like a really good proof of concept. What are the learnings that you gathered from those days, and how do you think this time can be different? You know, what are you guys doing different, or what you've learned from that project that could help you improve all this?
Yeah. Yeah, the original concept was Oberth in 1929, or that's what most people, cite the discovery as. NASA's research into this in the 1970s was really compelling. They did the whole thing. They did like all the reflectors, everything, and even a number of papers by France was, they were just incredible papers. And they basically laid out the whole thing. They were like, it's going to cost $500 billion to make this, but it might be worth it. Obviously, $500 billion is quite a bill to foot, especially for the U.S. government as they were ramping down their space travel. But even back then, in the 70s, launch, it was like almost 100 times more expensive than it is today, right? Like we have the Falcon 9, it's $6,000 a kilogram. Actually, back then, if you used the Saturn V, it was pretty cheap per kilogram because it was such a large vehicle. But even if once you got the things into space, there was no solar on the ground to actually receive it. And even in the 90s, when they launched Tsunami, there was about 200 megawatts of solar around the world, according to some research that I did. And 200 megawatts is like a fairly small utility scale solar farm today. We have about 2 terawatts of installed solar, so it's 10 to the 12 instead of 10 to the 6. So it's quite a lot larger. 6 orders of magnitude more solar today. About $3 trillion worth of solar is built around the world. So you have the launch side with SpaceX, and I think SpaceX it's more of like a availability than a cost thing for us as well. Like even when I was interning at SpaceX in 2016, I remember thinking of like, wow, this whole rideshare thing is incredible. You can just send stuff into space and it's really easy. And I had never thought of it like that before working at SpaceX. I was like, you can't send stuff to space. It's going to be super hard. It's going to be very annoying. Like even the CubeSats that NASA would launch seemed really problematic. And like, sometimes they would sit on the vehicle for a couple years before launching them. And it was just like, oh my God, how do you deal with these horrible constraints? But then at SpaceX, I was just like, wait, all these constraints actually are pretty reasonable. Like it's not that hard to get something into space. And it was just mind blowing. And that was just the 2016s. So this really hasn't been like easily tractable for a very long time. Like you haven't had the insane amount of solar. Because on the solar side, even in 2009, solar was like $359 a megawatt hour, which is like twice the price of nuclear. But today it's in the 30s or 40 dollars per megawatt hour, and it's actually the cheapest source of electricity. It became the cheapest source of electricity in 2021. So none of that was a thing even 10 years ago. And 20 years ago, forget it. And then 30 years ago, that was when Tsunami was up. So back then they were actually just using it, the only application was lighting up large areas. So like lighting up giant mines in Siberia so you could mine, in the Arctic nighttime. And they launched it up. They had really poor note keeping on the ground. It was like about a full moon of brightness. But like when it was flying over Europe, it was cloudy and like nobody measured it. And there's like one video that we keep seeing that was from Florida, and it's unclear if that was like a real video or a fake video. It's kind of hard to tell. We're still trying to figure that out. But yeah, it was, they still did it. They launched the vehicle, and they actually tried to launch a follow-up vehicle that was a little bit larger, but that one failed on deploying. And it wasn't even a failure of like the reflector. They just deployed the antennas before they deployed the reflector. So
got stuck with the antenna, right?
Yeah.
It was the 2.5?
But the antenna wasn't supposed to deploy until after the reflector. So it was like a dumb failure.
Okay.
It was like hitting the brakes and the accelerator at the same time, kind of.
Sure.
Like, but unfortunately it killed the program. But even back then, launch was so expensive, and basically all we had in the US was shuttle back then, which was in the 30s of thousands of dollars per kilogram instead of, ride shares are 6,500 a kilogram, and then, launch is, 2,500. So like, if you can buy a whole Falcon 9, it's an order of magnitude cheaper today.
Mm-hmm. Let's talk about the technical stuff. So you have that Earth globe there. I just love the model. Can you grab it? I would love to talk about the orbit that you guys are going to be using. I guess it's a sun synchronous orbit.
Yep.
An SSEO.
SSO, yeah.
SSO.
And it's a bit of a special SSO. So if you imagine the sun over here lighting up this half of the Earth with the shadow here, usual SSOs are, right like this. They're at like, 10 a.m. or something like that. So you can take a picture without a shadow on the ground. Our orbits are clocked 90 degrees to that. So we're riding the terminator. We're always over the terminator line, which is the shadow of the sun on the Earth.
So that's the division between the sun and the shadow, right?
Yeah.
Areas.
Yeah, I mean, nighttime is really just a shadow.
Yeah, sure.
It's no more complicated than a shadow. It's just a really big shadow.
So, okay. So that's very smart. One of the things I thought when I was, preparing this interview is that you guys are going to be, because those orbits are around 90 minutes,
Yep.
and that you are going to be getting some sort of eclipses going on, but apparently it's not the case.
We don't get eclipses on the ones that are really riding the terminator, but we do on the later orbits. So when we go later into the night, we crank the RAN back, and then we increase the altitude a bit. And then when you do that, your inclination changes so that you can stay SSO up until the point where you're high enough that you actually just want to be in a standard orbit. But yeah, then those will be flying through Eclipse sometime. So we are flying prop on our first vehicle, and we'll be flying prop on all of our satellites. Just to the main reason there is to move around in space and move around quickly so you can dodge objects. That allows you to add more satellites into space. And the more maneuverable you are, and the better your data is on where your position is and where you're going to be, the more satellites you can add to an orbit. So prop is critical for that, so we're flying prop anyway. But theoretically, you could solar sail and maintain orbits indefinitely at our altitude.
Yeah, I was about to ask you, what active control mechanisms do you have in place to ensure precise pointing? And how do you avoid oscillation or jitter in the mirror plane?
Yeah, so most of it's all just the same stuff that people use in normal satellites. A lot of times in optical satellites or telescopes, they'll have piezoelectric, real-time correction for vibrations. We don't even need anything like that. We just do the main, spacecraft body position control and body position estimation. And just with all the same, normal star trackers that everybody uses, normal reaction wheels that everybody uses, we actually are, perfectly in line with the accuracy that we need. Because it's such a large spot on the ground, it's about 6,000 acres or just under. It's okay if it's off by, hundreds of meters. It's not going to really affect the spot too much. But even with that, we can be well within that with just normal hardware. And the mirror itself it's obviously a semi-flexible body because it's a large tensegrity structure, but because we have so much compression in the booms and so much tension in the reflector, it's fairly stiff. It's stiff enough to get around. And the maneuvers, while it's just a nadir pointing maneuver, so it's a nadir pointing reflection, so it's fast, but it's not that fast. It's not like we're repositioning in like a second. It's 30 seconds or so to reposition within a really large, couple 100-kilometer diameter area. And then most of the sweeps are, over the course of 4 minutes, and it's a pretty smooth sweep. There's not too many sharp points in there. So the reflector is able to, stay fairly under control.
So how are you guys planning to cope with the drag? How is it going to affect you?
So we will saturate our reaction wheels slowly due to drag, because you're going to have a different, you'll have a different force on one side of the center of gravity versus the other, and that'll just slowly increase the saturation of the reaction wheels. So we'll basically just be spinning motors faster and faster to counter that. And it's like reaction wheels work in the same way. If you've seen a dirt biker, they jump up into the air and they'll hit the accelerator to spin up their back wheel, and the dirt bike will pitch back, or they'll hit the brakes and the dirt bike will pitch forward. We're doing the same thing in our satellite. We have some very large momentum wheels, and we just, they're attached to brushless motors, and you spin them up in one direction or another to change the rotation of the satellite. Or if the satellite would want to rotate, you can keep it from rotating with those. And then we have magnetorquers to desaturate those, some very large magnetorquers for this first satellite to desaturate them very quickly. And those basically just use the Earth's magnetic field as a stator, and then it's like a simple motor. It's actually the same thing that's making this Earth rotate. These are great. You can just buy these Earths on Amazon, but they have a little solar panel in there and a magnetorquer. So in the same way that this is rotating, it'll desaturate our reaction wheels. And that works in low Earth orbit. It doesn't work around other planetary bodies. Like we can't use magnetorquers around the moon. So there we have to do other things, or really just use prop, and then you just end up with a certain lifetime with your prop budget. But yeah, on Earth, we have the Earth's magnetic field, so we have magnetorquers, and they're just solar powered. And then the reaction wheels, which are actually steering the satellites, are all just solar powered as well. So yeah, the only thing we need prop for is changing our orbit to dodge debris, or if we end up lower in the altitude than we expect, boosting back up.
So optics here are really important. What type of materials are you guys using for the reflectors?
Yeah.
It's a mylar material. How are you going to deploy it?
Yeah, so we say Mylar, it's really a thin plastic, and we don't publicly share exactly what the
Sure,
material
of
is.
course.
It's actually, there's several herbs and spices going on in the material, but it's a thin plastic, so it's not like a giant piece of silicon, or it's not like the James Webb, it's not like beryllium. It's quite thin. It's 2.5 microns is what we're doing for the first one, which is actually difficult to handle with your hands. But when you get it into space and you tension it, it's never being touched, so it's quite nice. And making it so thin allows the satellite to have a really low moment of inertia, so it can move around quite fast with low mass. And it's also lighter to launch as well. The whole reflector is like less than a kilogram. And yeah, we tension it with the booms, so that's critical. Just to get it this tensioned. And the way we fold it up and deploy it is very specialized. We have an origami expert in-house, Robert Salazar, who's done an insane job doing all the development and testing for how the mirror actually deploys and folds up. And there's a number of herbs and spices in that as well, in how it's actually folding and unfolding, and maintaining its flatness and specularity throughout that whole thing.
Then how do you deploy? We go backwards a little bit, but how do you deploy? I don't know if you can show us. How do you deploy the satellite? When the reflector. How does that work?
Yeah, it's very. So this is the model I like to show for deployment. And everybody's familiar with a tape measure, right? You extend the tape measure out of the little roll, and the tape measures are able to kind of roll up around a drum. So we're doing a very similar thing. We have large carbon composite structures that are similar to tape measures in the fact that they can fold flat and then roll up. And then you basically just unspool these off of a drum, and they deploy out, and then you fix them in place. And they can take, our booms can take about 1,000 pounds in compression. So just like, pushing on a tape measure can take a certain amount of force. Because this is an open cross section, you have a lot less torque. You have a lot less torsional rigidity. So you end up having a much lower buckling strength of this. When you actually close this off, it gets much stronger. So we do that, and those unroll out. And then the reflector deploys out, kind of like hoisting a sail on a sailboat. It's just on strings. You just, pull that thing out and then pull it tight. So it's like tape measure technology and sailboat technology for the whole reflector. And then, yeah, we have 4 of these quadrants, and you can see the size of the real ones behind me. So all that's pretty simple. And then to move the satellite around, it's the same reaction wheels that you have on any satellite. This is obviously just made out of quadcopter parts. But it's really the same thing. It's a motor and a wheel. And when you spin the wheel this way, equal and opposite reaction, the satellite rotates that way a little bit. And then if you just keep spinning this faster, for every increase in RPM this way, you get like a little bit of movement going this way. So we're able to do that and just fully move the satellite around. And then obviously we have the magnetorquers and the prop system, like every other satellite has. And yeah, that keeps us where we want to be and pointing where we want. But yeah, the actual reflector deployment is quite simple in principle. The secrets of how we do it, to keep the reflector flat, we don't share. But yeah, you can imagine this whole thing, the whole boom's deploying out of there, and then the whole reflector deploying and then being tensioned.
How concerned are you about maintenance? You have all these things happening up there, micrometeorites, you have radiation, you have many things happening, and it seems like a fragile mechanism, right? So how concerned are you about that?
Yeah, so the actual reflector can take micrometeorite hits without ripping over a large area. You basically just get the whole puncture, and then it doesn't rip larger.
You showed us an example. That's pretty cool.
Yeah. So if you poke a hole in this, I just poked this with a screwdriver. Yep. It doesn't rip over a larger area when it's fully tensioned, and that was critical. So finding materials that have these properties is critical. There's some materials that would just explode immediately or like rip all over immediately, but find ones that don't. And then the area doesn't decay that quickly due to micrometeorite impacts. It's like you can stay up there for decades. It wouldn't really be a problem. The larger problem for us is atomic oxygen. We have coatings to prevent degradation from atomic oxygen. But really, like these materials are, I don't know if you've seen a satellite, they're always wrapped in that kind of shiny thermal blanket stuff.
Sure.
This is the same stuff. that's on every satellite, or pretty much every single satellite has those MLI blankets around them. We're launching that into space, we're tensioning it, but it's those same materials, it's those same techniques. They're covering every satellite already. We know how they behave in space. There's like physical examples that have been in space for decades that we can look at. And yeah, so luckily we don't have to figure that out. I think that's overall with this idea. A lot of times with new ideas, there's all these brand new things to figure out in physics problems. With this one, basically everything's been solved in isolation at some point along the way, and we're just combining it all together for the first time, which is really exciting. So yeah, even the materials are extremely space proven. MLI blankets are on every vehicle. So that's really well understood. I think for the rest of the components, I think avionics for spacecraft still have a long way to go, particularly radiation hardened avionics. If you need, just a normal processor, like some of our processors are like $30. But if you want stuff that's rad hard, that's good to like 100 kilorad for going out to MEO, those are in the tens or hundreds of thousands of dollars. Like you can easily pay $200,000 for a processor, for a rad hard processor. And it's not like it's taking up that much more silicon or germanium or silicon carbide or something. It obviously, like, those materials are more expensive to fab, but really, like, we could make that whole thing a lot cheaper if we had more volume. And our satellites won't really be enough volume. Like, even if we're talking like 10,000 satellites, that's not very many laptops, right? Or not many phones. Like, we've built billions of iPhones. So those are the kind of volumes you need to really get the cost down for avionics. We're going to be a small part to pay. But I think the more we can build spacecraft with commercially available components, the cheaper they're going to get. And the avionics have, I think, the highest. Elon uses the idiot index, which is kind of like the cost of the thing divided by the raw material cost. I think avionics have an extremely high idiot index. It's in the hundreds at least. So that one's quite large.
Are you guys in touch? I mean, when we came here for the first time, we visited VAST, which they are not far away, building what's probably going to be the first international space station, launching next year. Yep. We have SpaceX just around, launcher that now belongs to VAST. Yep. So there's a lot of things happening in this area. Are you guys in touch with other companies? Because I see synergies in you guys talking and probably helping each other, or if it's that off the table.
Yeah, I think one of the more exciting parts of being the CEO of a company like this is you kind of meet everybody.
Yeah,
I didn't expect that. It's been really cool. I know the leaders of most of the companies around. It's awesome, and talk about all kinds of different things. I'm not gonna announce anything here, but yeah, we're exploring a number of partnerships. Obviously, we talk about our ride up to space next year. That's with SpaceX. That's just a normal ride share. That one's pretty straightforward. It doesn't require much for that. But yeah, we're talking to everybody, and the Hawthorne area is really great, and in the greater Los Angeles area as well. When I was here in 2016, I kind of fell in love with it and how many space people are here, and how many aerospace people are here. Everybody knows how to, just get giant hardware together very quickly, under extremely strict timelines and, design parameters, like, just really strict requirements. You have to be really rigorous, and everybody here understands that rigor. I was in San Francisco for a little while, and you'd meet people there who didn't know what a CNC machine was, and it was like, what on earth is going on? And then where I grew up on the East Coast originally, like the most successful people in my hometown were dentists. It was like very, very, very different than starting companies, and especially aerospace companies. So yeah, the LA area is just incredible. There's just like thousands of people who are, who've built aircraft for 40 years, or who've, worked at SpaceX for decades. And it's just like, the talent here is insane. And we love just being one of the companies here. And it's also great for just getting things done, right? So like, all the materials vendors are here, like, all the technicians are here. Like, there's just so much resource in LA that can support a company like us. And you just don't get that everywhere.
What about talent? I guess you guys are hiring talent at the moment. You have fresh money, so I guess you can do more things. Which type of profiles are you searching for? Why should someone join you?
Yeah, we're really looking for people who believe in the mission. I think that's the biggest thing. We want people who see this as critical path to a Dyson sphere. We want people who are bought in on not just Reflect surviving, but this concept being a thing in the world, and people who can really get behind that. I think that's, that's kind of the main thing. If you want this to happen, like, come join us. I think the other thing that we look for is people who work on a lot of projects in their free time, like people who kind of have reverse writer's block, who just constantly have ideas and are constantly looking into them, and doing really great work along the way. Yeah, so that's really important. And I think like our team right now, like we get a lot of inbound, because like, I don't know, we've been all over the internet and stuff. So we get thousands of applications, like, just constantly. And that's been great because we've been able to be very selective with the people that we do let onto the team. So not only are we looking for, the best of the best in design, like sometimes we're able to hire like the one of one person in the world who's just spent their whole life honing a skill that like we have a need for. So we've been able to find those people, and they've kind of seeked us out as well because they've heard about us a little bit. So that's why we're continuing to do media stuff. It's because it's incredible because people hear about you and they're like, oh my gosh, this actually solved this problem that I've had for most of my life. And then they, they're obviously incredible, because they've been thinking about things outside of work. They've been spending their own time reading books and learning about something and becoming an expert without anybody asking them to. They're not just doing their job, they're doing everything. They've become obsessed with a certain idea and they've been chasing it. So that's obviously a requirement, but we're also able to find people who've been obsessed about chasing ideas, who understand some critical component of our satellite. So we're able to hire those two things, which is huge. I think a lot of it's very hard to get that. It's very hard to get the incredible talent who also believes in the mission, who also has a specialty in the field that you're looking into. I think just like the fit that we've been able to get on our team is really incredible. We've done an insane job. It's really hard to hire people that are that perfect for what they're doing, but it's so worth it. Because like, you'll hire somebody and just all your problems are solved. Like we'll be like, oh my God, like this whole thing is gonna break, like everything's gonna fail. We have no idea what we're doing. We feel like a mess. And then we'll just hire one person and then everything is just completely fixed in like 3 weeks. Like they've just solved all the things that we were worried about because they're excellent at that thing. And yeah, I've been at companies where that's just not the case. Where like the people you bring in don't do anything really, and they don't really help further the mission. I think here, like we've just been so incredibly blessed at like really looking for people that have the right things. People who like are interested in just doing real science and doing real work and having a real impact. And they just run. And one other thing that I think is really important is it's not so much like people are here to serve or like Reflect Orbital, like this company, like, it's just a company, like whatever, like it could fail, it's a startup, who cares? But it's, if you're here because you want to do the best work of your life, like this was a thing I saw at SpaceX, like you go to SpaceX because you want to do the best work of your life. You're not actually trying to further the mission of SpaceX. And a lot of people are, trying to go to Mars, but in a lot of ways it's for yourself, right? It's like going to a really good school. Like if you go to MIT or Stanford, you're not there for Stanford or MIT. Like they're not even they're profiting from you being there, but you're actually paying them. Like you're actually giving them money. You're not getting anything in return apart from the education and the experience. And I think people join SpaceX for that thing. And we're interested in people joining here for that same thing, where you want to be here for the experience of working on stuff like this, on giant heliostats. You want to build the Dyson sphere. You want to increase humanity from Kardashev 1 to Kardashev 2. You want to give us control over the sun at night. You want to be able to light up crops anywhere on Earth and change what climate plants are in. You want to add this new capability that's never existed in the world, where you can just light up anywhere on Earth, the touch of a button. Basically like as easy as sending a text message. You can send some physical stuff, some really powerful physical stuff anywhere on Earth. So people who are interested in building that capability for themselves, for their own selfish reasons, like you can come and spend our money on insane technology. And basically it's like, one thing that I always thought of it, about getting a job, like even getting a job at SpaceX, it was like all the money that you get to spend for the company is kind of like your own personal project money. I think that's the best way to think about it. Where if you're like, hey, I'm gonna go to Reflect and I'm gonna buy this cool thing and I'm gonna put it together and it's gonna be super helpful. It's all gonna be with Reflect money and I'm just gonna get to build this really cool stuff that does this really cool thing. that's the kind of feeling that you like lean into. That's what makes you do incredibly well, is when you're in it kind of for selfish reasons almost, but obviously selfish reasons that are extremely well aligned with progress happening in the right direction. That's everything.
And Ben, I'm glad that you mentioned that, because when you get to read a lot of the reactions on social media about your project, guys, you know, there are concerns about many different topics, right? That I guess you guys are working around those in terms of PR. But one is, you know, of course, astronomers will be like, we don't want to get more disturbance, you know, with satellites there that will ruin our observations, or nature. I mean, there is a cycle, day and night for a reason, and we don't want to get, you know, nature or even plants, you know, that they need the night, you know, to do their thing.
Yep.
So how are you guys planning to overcome those worries? I mean, you made now a comment about how precise you can be. So I assume people won't be getting light where light is not needed, and those things can be avoided. Is that correct?
Yeah, absolutely. Yeah, I mean, our spot, you know, you say 6,000 acres, it sounds really big. It's about a 6 millionth the area of the surface of the Earth. So if you look at it on a map, it's really tiny. I mean, yeah, so people get concerned about the area because you say 6,000 acres, and they're like, that sounds gigantic, right? But it's actually about a 6 millionth the area of the Earth. It's similar in size to the Palm of Dubai. And if you ever look at a map and you try to see the Palm of Dubai, you really can't see it. It's like, you know, a pinhead. It's super small. So that's the size of our spot. And we can very precisely control where that's going. And then we can go from, you know, one spot to the next without lighting up the areas in between, right? We can detension our reflector. So we can just light up so many precise little areas without lighting the area around them. And, you know, astronomers, the main concern is that you're going to blow out somebody's image, right? Like with Starlink, it was a terrible disaster because Starlink satellites fly over and they're kind of a diffuse reflector because they're serving telecoms. So they're reflecting light over basically the whole Earth underneath them, kind of accidentally. And like they're trying to get the reflector better and better, but it's still hard, you know. And every satellite you see is reflecting sunlight down in their diffuse reflectors, so it's over pretty much the whole area underneath them. We're entirely different. We're extremely precise. All the light that hits our satellite is going in one precise spot, and we can rotate our satellite to reflect sunlight away when we don't want to light up a spot. And this is how Starlink actually, you know, solved the brightness problem, is they put little reflectors in front of it that reflect sunlight away from the Earth. But our whole satellite is basically like that, and we don't have any other equipment on board that's in view of the sun. So it's super dark. So if we're flying over, you know, say Chile, in a very large telescope, you know, up on top of the mountain up there,
Yeah.
you know, we can just stay, you know, miles and miles away from that site. And when we do pass overhead, we can just reflect all the light away from the Earth as we fly over. So we have a ton of control over where the light is going and where it's not. And I think the broader issue is, so say if somebody does want sunlight, right? Like if you do have a city that wants sunlight, you're going to mess with circadian rhythm. You're going to, you know, and, you know, everybody worries about you're messing with circadian rhythm, or, you know, you're lighting up animals and stuff like that. But I guess for a large city, we're already choosing to do that with street lights to a certain extent. And we can just directly replace that with a better solution. And I think one thing that people don't realize is with street lights, you're actually over brightening the area underneath the street light. Like it'll be about 20 lux or something like that, even though you're trying to hit 3 lux in between the street lights. So you have all this extra light under the street light, and we can just hit 3 lux over the entire city. And the other thing is the bulbs. Usually when you look at a city at night, you're seeing bulbs everywhere glaring in your eyes. And those are actually a lot brighter than the ground that they're lighting up. With us, the satellite is way overhead, so you can't see it. And then we can just fill the entire area with that 3 lux. So you're not over brightening areas. You don't have the glaring bulbs that point straight into your eyes and also look really sharp. And you can't see the vehicle at all. So when we are lighting up a city, actually it's likely to be much less light pollution if you're doing an equivalent replacement. And if you're doing it in a new area, you don't have to trespass on everybody's property to build all the lighting infrastructure. You don't have to pay for any of that. And if you want to cancel it, you can cancel it immediately. I think another thing is a lot of cheap street lights don't have control over when they turn on and off. And even when they do, sometimes it's like a little solar activator or something like that. It's kind of hard to implement. With us, we can dim the lights at night. We can turn them off at night. We can have them over very precise areas. So we have so much control over where and when we're lighting up areas that you can really minimize the negative effects. And if somebody does choose to light up an area, it's very likely that we can do it in a much better way than the streetlights that were there before. That said, if you're lighting up, like a farm or a solar farm or something like that, that's like either a monocrop species, like you're lighting up a strawberry field or something like that. There's just strawberry plants there, plus some animals and stuff. So it's a lot easier to, compute the impact. And in places that already make sense to light up at night, like dragon fruit farms, where they have just, hundreds of LEDs. It's actually crazy if you look at the pictures of dragon fruit farms. They use LEDs to do photoperiod manipulation. So the dragon fruit plants think it's, the summer when it's the winter. And they get this little bit of extra light, and it changes how much fruit you're able to get from the same amount of acres. So we can do a similar thing, and the light impacts of that are already very well known. We can just do it without all the wires and LEDs on top of every single plant. So it's actually a much lower impact, even in that scenario.
So Ben, you're here to make money. What would you tell people who are actually really concerned about things going wrong? Like, what would be your pitch saying, guys, we know what we are doing. This is not going to be harmful. We all have in our minds movies from James Bond, building those crazy solar weapons that could destroy. Even Archimedes, there's rumors that he was planning to use reflectors to destroy ships. What is your message to those people who are concerned about this as an idea?
Yeah, so we're not going to light any fires. To light fires, you need to be quite a bit brighter than the sun at noon. So it takes a lot of very deliberate efforts that you would definitely be able to see. Like you'd be like, wow, these guys have 50,000 satellites in this one spot that could light fires. Like, okay, we're not going to do that. That would be completely insane. We want this to be something useful that people can trust. And it first of all, it just takes a very long time to even get there. But second of all, there's no reason to do that. We're focused purely on the positive impacts. I think that's how you create something that's going to last for a very long time. Like when you kind of want something that's almost uncorruptible in a way. And the closer you can get to an uncorruptible technology, the more likely it is that when you die and other people take over for you, it's still going to be a positive thing for the world. So I think we got very lucky with Reflect that it is kind of this uncorruptible technology. And I think that was one of the things that I'm really proud of is I feel like when I die and hand this off, other people will be able to take it from there and do the right thing with it and not really corrupt it. So, just making sure that you don't have so many satellites in a spot that you can light a fire is a huge thing. Another thing is just being really selective about where you're lighting up around the world. So we're being very proactive with, trying to talk to everybody who's an expert in the field of light pollution at night. So we've talked to a number of experts and we're doing a lot of research. And when we launch our first satellites, we're also going to be able to do real measurements and really see exactly what the impacts of this light are. And with that information, we're going to be able to figure out where we do want to light up and where we don't want to light up as we build up the constellation. And I think the feedback from the world and the global community is everything for this. Like when we light up a certain area and it's only good, like we're going to continue to lean into those places. But there's going to be some places that we're like, hey, we don't want to light up, areas like that anymore for these very clear reasons. And if something changes, then maybe it would fix it. Like maybe if we block some of the ultraviolet light, some things would be fixed. Maybe if we just decrease the light level, some things would be fixed as well. Most species aren't very affected by light if it's under 0.1 lux. So if you just reduce the light enough, it's actually completely fine, and that's something we can do. Or if you just change when the light is turning on and off, that can also change, how birds are affected. For example, when lights, turn off, sometimes the birds stop going towards the city lights. So there's a number of controls we can implement on the technology side to make this, a better, more holistic solution for the current climate and the current world. Because really, the better we're able to match the current world's needs, the bigger our company is going to grow. I think it's very short-sighted to be like, oh yeah, we're just going to send this thing up and figure it out. We want to do this right from the beginning so that we can grow faster in the long run and figure out all these controls as rapidly as possible. And there's some things that are going to be a little bit risky. And you have to weigh out for each one of those if it's worth the risk or not to just try it. I think in some cases it's, fine to just try things for a short amount of time and just see. And if you don't like it, we can turn it off immediately. I think that's the biggest thing with this. It's not like we're building street lighting infrastructure that you're going to be stuck with for 30 years. You're going to be paying the bill every single month. You know, you'll see it on your, you know, on your taxes. Well, this is very different. If it's not good, we can turn it off actually in seconds. It doesn't even have to be the next day that we don't turn it on. So I think the amount of control and responsiveness that we have with this light is going to allow us to learn a lot faster and learn in a very healthy way when we're proactive and when we're trying to talk to everybody and when we're really reaching out to communities all around the world, all different nations, like all different stakeholders at the table. I think that's the way to do it. That's what we're doing. It's, you know, it's a lot, like but it's so rewarding. And if we can get this right, the impacts are going to be enormous. I think, you know, sunlight at night is one of those things that humans will always eventually do, right? Like this is definitely a thing that's going to be around in a couple thousand years. And there's really no reason why it can't be around next year. Or even just a couple years after. Like the world is ready for this. It's just nobody's thinking or talking about it yet. So we're having to start all these conversations and do all the talking first. But other people are going to take over. Like you're going to see research groups take over, universities take over. Obviously, they can use our satellite as well. We can arrange that, like reach out to us if you want to do a study. We can do studies in your exact location with our exact satellites, and we can figure out exactly what the impacts are and if it's worth it or not. And that's something that you'll be able to decide on your own. And then obviously, if it's not a good thing, we won't serve it. But if it is a good thing, we obviously will. So we're going to be doing that, you know, with thousands of places around the world simultaneously over the next couple of years. So it's a massive undertaking, but oh my God, it's so cool. And
because still it's the cheaper you can get a kilo up there is like $6,500.
Yeah. And
so
you're also
it's hard to compete with batteries that are already on Earth.
Yeah. And you're competing with a commodity as well, electricity. And honestly, people don't really care about cheap electricity. Like you care a bit at the big scales, but at small scales, really, you just care that you have the electricity, right? So it's a commodity. It's a really tough market. The thing that's cool about it is it's huge. It's trillions of dollars per year. But it's really hard to access. And I think like that's why you don't see too many energy startups that are doing something brand new, because it's so hard and the capital required to get there is actually really difficult. But the cool thing with us is because we're not just providing electrons, we're providing sunlight, we're providing photons. And humans have a use for even very tiny amounts of that sunlight at night, which we currently have no way to get. So lighting up areas is just, it's hundreds of thousands of times easier than, you know, providing electricity. So we can start with that when the satellites are really expensive. So this first satellite is a couple $1 million, right? We're launching it at, you know, it's like twice the price of a full Falcon 9, and then, you know, we're going to see Starship soon and everything's going to come down even more. Yes. So we can do this when it's really expensive. We have markets for it. We can make money with those, just lighting up areas at night, giant areas, this huge new capability. And then we can increase the amount of square meters we have by just launching more satellites. We get even more lighting customers, even more revenue. And then we start to unlock new things, right? So the first satellite, it's like the 4-minute flyby. It's just the beginning, right? It's just, you know, it's 4 minutes. It's hard to time it, right? You have to be there at the right time. You have to show up at exactly the right time to see it. But then when you do 18 in a ring, it's an hour anywhere on Earth twice a day. So then as long as you're in that hour, like, oh, it's between 6 and 7 p.m., then you can get satellites, right? And then we add more rings. We'll add another ring for another hour. And then we'll add rings all night. When you have a couple hundred satellites, you can do all night service. So then you can get sunlight anywhere on Earth, anytime at night. And then that's an insane new market. And then we can just increase the number of satellites in that shell to serve more customers, because each satellite only looks at one customer. And you only need about 60 customers for the satellites to break even. So it's actually quite interesting. And then you just like keep building that out, because there's thousands of customers out there. So like 60 each is really minimal. So then you just keep building those rings out. And then all of a sudden you have enough satellites to start serving energy. And you've already launched so many satellites that you're able to get the costs down. And around that time, we actually expect Starship to be operational as well. So it's another huge cost down. And then it's like, wow, this actually will make sense for energy at that point. So that's how we get there. Is we have this whole trajectory where we basically can crawl, and then we can walk, and then we can run. And we're really blessed to have that with a lot of technologies, like, you know, if you're doing a fusion reactor or something like that, or even just like a normal fission reactor, it's, you know, to make one big enough that's going to work and operate, it's pretty difficult to figure it out. And there's a lot of the small modular reactor guys that are figuring out ways to do it small. But I think we were able to do that in a very fundamentally pure way, where you start with just a small amount of photons, and you find people that are able to pay extremely high amounts for those photons because it's worth it, because you need those photons, because there's some critical applications where you just need some light at night and there's no other way to get it, and we can do it infrastructureless. And then you just slowly build out from there, and you just like find people along the way. So I think like, you know, there was a world where we just only focus on energy, but we would just miss so much along the way. So we took the time before we even launched the first satellite to spend a lot of effort to really find all these tiny little steps along the way, to make sure we had this, you know, fully coherent go-to-market plan. It doesn't have holes in it.
So Ben, it's been a pleasure to talk to you today. I want to give you the patch of our show.
Oh, thank you.
Orbita,
Wow.
thanks for having us. Yeah, we wish you a lot of luck. Luck never hurts.
Yeah.
So, and it's always welcome. But as a futuristic, I love the idea. So I would love to follow the project along, and I wish you all the success of the world. So thank you.
Yeah,
thank you again.
Pablo.
Thank you.
Bye-bye.